Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So we're going to continue our study on the geometry treasure, Orthocenter property B2. And for the B1 video, which I think I released it maybe last week, and that contains about 10 properties of a figure. And now let's continue our study. It's about another 10 properties of the same figure, but let's just repeat the problem set here. Okay, H is the orthocenter of non-isosceles triangle ABC. So let's just draw the circle first. And we have a triangle. A, B, C here. Right. And projection of H on BC, CA, AB are D, E, F respectively. O is the circumcenter of the triangle ABC. M is the midpoint of BC. Circle M is a circle center that M with diameter BC. Line MH meets circle O on A1, A2. M is in between the A1 and H. J is a midpoint of AH. Circle J is a circle centered at J with diameter AH. Prove the rest apart. Okay, so let's just draw the figure and see what the problem set is. So we have the circumcircle here, and this is our triangle ABC. Now we find the orthocenter. Here is D. And E. F. This point is H. And we know the circumcenter is O, and the midpoint of BC is M. Midpoint of AH is J. And we connect MH. Right. This line meets the circle A on A1 and A2. That M is in between A1 and H. So in the video, now the problem is asking us to prove that A2JOM are cyclic. Okay, so in the B1 video, we actually proved some properties already, so I'm not going to repeat it. Please refer to the B1 video. Here I'll just use the conclusion. The conclusion is like this: BA1CH is a parallelogram, and also AOA1 are collinear, which means AA1 is the diameter of the circle O, and also A2, A, F, H, E are cyclic as well, right? The A, F, H, E are cyclic is straightforward just because this is 90 degrees, this is 90 degrees. And for A2 is also on the circle J because A1 is diameter of the circle O. That means the angle A1, A2, A is 90 degrees, which means the angle H, A2, A. So let's actually connect this one. H, A2, A is 90 degrees, right? And we already know that AH is the diameter of the circle J, and here the angle A2H is 90 degrees. That means the A2 is also on the circle J, which means we already have the conclusion that AF, H, E, A2 are cyclic. right? Now we want to prove that A2JOM are cyclic. So we connect OM. We already know we connect OM, OJ, and JA2. We already know that OM equals to half of AH equals to JH, right? Equals to AJ, which equals to JA2, right? That's what we already know, because for the property of the Orthocenter, we know that OMHJ is a parallelogram. So we get these properties that OM equals to half of AH, because AJ equals to JH, right? This is a parallelogram, and JA2 equals to JA. That's the radius of the circle J. So we know that OM equals to JA2, basically here. And because OJHM is a parallelogram, that means OJ is in parallel with MA2. So A2JOM is an isosceles trapezoid. That means A2JOM are cyclic. Right, acyclic. Okay, that's property 1. And for the property 2, EF are on circle J and circle M. EF are on circle J. It's obvious. It's also on the circle M. Circle M is a circle that's centered at M with a diameter BC. Because this is 90 degrees, this is 90 degrees. So we know that EF are on the circle M. Then we want to see here, if line AA2 meets line FE on point P, then P is on BC. And H is the orthocenter of triangle AMP. Okay? It seems that we want to find the point P based on the intersection point that of the line AA2 and the line FE. AA2 and FE. If we find that point P and we want to prove that this point P is on BC, which is actually saying that we want to prove AA2, FE, and BC are concurrent. Right? We want to prove this one. So if you look at the figure, because FE are on the circle J and circle M, that means FE, or let's say this line FE is a radical axis of the circle J and circle M. Right? Line FE is radical axis of circle J and circle M. That means if we just draw a line here, right, meets AA2 on a point, this point is P. This point is P, right? On point P. Then we know that P has a same, because P is on the radical axis, so the power from P to circle J equals to power from P to circle M. right? And the power of P to the circle J is PA2 times PA. So PA2 times PA. And it's also equals to PE times PF. Right? Now the question is that how can we prove that it equals to PC times PB? Right? If it equals to PC times PB, then we directly prove that. So the idea is like this: we can neglect this point P first. It means that we don't have to, because we want to prove that AA2, FE, and BC are collinear, and we already know that FE is the radical axis of the circle M and circle J. So if we do it like this way, it would be more difficult, right? The thing is that let's think about P as the intersection point of the BC and AA2. Okay, P as intersection point of BC and AA2. Because AA2, CB are cyclic, they are all on the circle O. So P as the intersection point of the BC and AA2, that means PC times PB equals to PA2 times PA. Right? PB times PC equals to PA2 times PA. Which means PA2 times PA can be taken as a power from P to the circle O, and also can be taken as a power from P to the circle J. That is saying the power from P to the circle J equals to the power from P to the circle M, right? PB times PC can be taken as a power from P to the circle M, which means that P is on the radical axis of the circle M and circle J, which means that P is on FE. That means AA2, FE, and BC are collinear. Okay? The problem 3. The question 3. If circle J meets a circle that contains BC as a chord on XY, then XYP are collinear. So this is saying that we have the circle J here. Let me try to draw this circle J. We know that it's passing through the H and the F. Right, that's a circle J. So it's actually saying that if we have a circle that passing through the B and C, that circle passing through B and C made this BC to be a chord, right? And that circle meets the circle J on 2 points, for example, XY. Then we want to prove that XY and P are collinear. So it is easy because that circle, the circle that passing, let me just, for example, here, XY is here, right? XY. So that is saying BC, XY are collinear. BC, XY are cyclic. So we have PB times PC equals to PX times PY. No, sorry. No, that was not correct. I should say it this way. So because B, C, X, Y are cyclic, right? So the power from then xy, the power from P to the circle M can be taken as PB times PC, and that we already know that PB times PC equals to PA2 times PA. So the power from the P to the circle M equals to the power from P to the circle J, right? And then we get PB times PC equals to PA2 times PA. Right, we already proved this one. And because XY BC are cyclic and XY A2 are cyclic, right? So we can think it as that XY is a common chord of the circle J and the circle that with BC as a chord, right? That's another circle. It's not a circle M, but let's call it circle M prime, for example. So circle M prime is a circle BC as a chord, right? Circle M prime is a circle that BC as a chord. So we know that XY is a radical line, XY is a radical axis of the circle J and the circle M prime. And we already know that P to the power circle M prime can be represented as PB times PC. And P to the power of circle J can be represented as PA2 times PA. And we know that they are equal. That means P is on the radical axis of the circle J and circle M prime. That means XYP are collinear, right? Okay, and I think we have this one. We haven't proved it yet. That we want to prove H is the orthocenter of the triangle AMP. It's straightforward, right? Triangle AMP. We know that AD is perpendicular to MP, and also A2 is perpendicular to AP. We know this, so that means the intersection point of AD and MA2, the point H is the orthocenter of the triangle AMP, which means PH is perpendicular to AM. And if you think that we connect AM here, then we know that this point, let's call it point S, right? The angle ASH is 90 degrees because AH is a diameter. And we know that PH, the line PH, form a 90-degree angle with the line AM, which means the SHP are collinear, right? SH is perpendicular to AM, PH is perpendicular to AM, so SHP are collinear. And let's see the problem 4. If circle J and AM meets on point S, circle J and AM meets on point S, that's actually we just proved it, right? Then SHP are collinear. We just proved that. And also MSA2P are cyclic with MP as diameter. MSA2P are cyclic. We want to prove MSA2P are cyclic. The first thing we want to check about is that Because this is 90 degree, this is 90 degree, we know that PA2 HD are cyclic, right? Remember, we want to prove that MSA2P are cyclic. But we know PDHA2 are cyclic. So the angle A2PD equals to angle AHA2. And angle AHA2 is angle equals to ASA2, right? Equals to this one. That means the angle ASA2 equals to angle A2PM. So MSA2P are cyclic, right? This angle equals to this one. Then we get A2SMP are cyclic. And okay, these are cyclic, and we also want to prove that MP is a diameter. It's easy because this is 90 degree, this is 90 degree, so MP is a diameter. And we also want to prove that BSHC are cyclic. Let's see here. We want to prove that I mark it as a star sign just because this is a property that not occurred on the book, right? It's a one that I derived. So we want to prove that BSEP, am I correct? No, BSHC. Yeah. We want to prove that BS H is here, right? HC, we want to prove BSHC are cyclic. So think about how can we prove that BSHC are cyclic. Before that, we just think about something else. We just proved that PA2 SM are cyclic, right? That means AP, it's better to use another clean paper. Okay. Okay. Remember, we just proved that SMPA2 are cyclic. Then we know that AP times AA2 equals to AM times AS, right? AP times AA2 equals to AM times AS. And also, we proved that PA2 HD are cyclic. PA2 HD are cyclic. So AP times AA2 equals to AH times AD. Right? So we have AH times AD equals to AA2 times AP equals to AS times AM. Right? And because this is 90 degrees, this is 90 degrees, so we know that B, F, HD are cyclic. B, F, HD are cyclic. So we know that AH times AD equals to AB times AF. Right? AH times AD equals to AF times AB. That's from B, D, H, F are cyclic. We get this. So based on this, we know that AS times AM equals to AH times AD. So MDHS, we got MDHS are cyclic. Right? And also because AF times AB equals to AS times AM. So we know that BMFS are cyclic. Right? It's not necessarily passing, O is not necessarily on the FS. So we know that BFSM are cyclic. Then the question is that how can we prove BCHS are cyclic? It's actually not related to these things, just because we already proved that SH passing through the point P, right? We just proved that SHP are collinear. So PS times PH equals to PB times PC. Right, so that means BCSH are cyclic, right? And we also get, let me write it down here. We just prove that because SHP are collinear. Right, how did we prove that? I hope you still remember SHP are collinear because SH is perpendicular to AM. PH is perpendicular to AM. PH is perpendicular to AM because H is the orthocenter of the triangle AMP, right? So PH is perpendicular to AM. That means SHP are collinear. And based on SHP are collinear, we know that PS times PH equals to PA times PA2, which equals to PB times PC, which means BCHS are cyclic. Right. Now we finish the problem 4. Let's see the problem 5. We want to prove that MSEC are cyclic. MSEC are cyclic. Yeah, it's cyclic because I haven't finished here yet, right? We already proved that AP times AA2 equals to let's do this. AA2 times AP equals to AH times AD because A2HDP are cyclic. And we know that DHEC are cyclic, so AH times AD equals to AE times AC. And also we know that BFEC are cyclic, so AE times AC equals to AF times AB. So we also proved that SMPA2 are cyclic. That means AA2 times AP equals to AS times AM, right? So if I just write it in one line, we know that AA2 times AP equals to AE times AC, right? Equals to AE times AC because AA2 times AP equals to AS times AM, right? And let's say AA2 times AP equals to AF times AB, and also equals to AH times AD. So AF times AB and also equals to AH times AD, and also equals to AS times AM, right? AH times AD equals to AE times AC, right? So all of them are equal, which means we want to prove that MSEC are cyclic, right? It's easy because AS times AM equals to AE times AC. So right, AE times AC equals to AS times AM. That means MCES are cyclic. And we also want to prove BFSM are cyclic. BFSM are cyclic, right? Because AF times AB equals to AS times AM, we just proved that BFSM are cyclic. And also we want to prove that PCEA are cyclic. PCEA2 are cyclic. PCEA2 are cyclic. Yeah, it's because AA2 times AP equals to AE times AC. So they are cyclic, right? It's basically saying for the combination like A2P, EC, HD, SM, FB. For these 5-point set, if you just choose any two of them, then the 4 points are cyclic. Okay, now we just prove this one. We want to prove that triangle A2EF is similar to triangle A2CB. Right, triangle A2EF is similar to triangle A2CB. This problem we actually already proved that one in the B1. But let's do it again here. Something like this. Right, we want to prove that this triangle is similar to this triangle. The question is like, how can we find the triangle A2BC? Right? How can we find the triangle A2BC? Because we already know that triangle A2BC equals to, the angle A2BC equals to angle A2AC, right? Because A2CB are cyclic. So we know that angle A2BC equals to angle A2AC. And angle A2AC equals to angle A2AE, right? That is, angle A2AC is angle A2AE. And angle A2AE equals to angle A2FE. So we know that the angle A2FE equals to angle A2BC. Right? And angle FA2E equals to angle FAE because FE, A2A are cyclic, right? Angle FA2E equals to angle FAE. The angle FAE is angle BAC. The angle BAC equals to angle BA2C. So we know that the angle FA2E equals to angle BAC equals to angle BA2C. That means the triangle A2FE is similar to triangle A2BC. Okay. And we also want to prove that triangle A2FB is similar to triangle A2EC. Triangle A2FB is similar to triangle A2EC. So the angle A2BF, right? The angle A2BF reference to the chord AA2 in the circle O, and that means the angle A2BF is angle A2BA, which is angle A2CA, right? Which equals to angle A2CA. So this angle equals to this one. And because in the circle J, the angle AFA2 equals to angle AEA2. That means if we use 180 degree minus angle AFA2, we got angle A2FB, right? And we use 180 degree minus angle AEA2, we got angle A2EC. So we already know that angle AFA2 equals to angle AEA2. Then we know that angle A2FB equals to angle A2EC. So this angle equals to this one, this angle equals to this one. Then we know that triangle A2FB is similar to triangle A2EC. Okay, prove this. And the problem 7. Circle J meets JM on T, then AT is an angle bisector of angle BAC. Circle J meets JM on a point T, right? This is a point T. Circle J meets JM on the point T, and we want to prove that AT is the angle bisector of angle BAC. Basically, we want to prove that angle FAT equals to angle TAE or angle TAC. This one is actually can be extremely difficult or can be extremely easy. So this one is only required an observation. Okay, let me do the connection here. If you cannot observe it, then it's extremely difficult. But if you see it, it's super easy. I feel it's very interesting. Let me repeat it again. J is the midpoint of AH, or the center of the circle O. Sorry, the center of the circle J, right? And M is the midpoint of BC. We connect J and M. The line JM meets the circle J on the point T. We want to prove that AT is the angle bisector of angle BAC. It might be quite difficult if we look at this figure because it's not clear for us. But if you think about what we have here, what is the point J? J is the center of the circle J. Then what is the point M? M is the midpoint of BC, but it's also the center of the circle M, which we didn't plot it here. But you already know that M is a center of the circle M. Circle M is actually the circle BFEC. So it's obvious that MJ is a center connection line of the circle M and the circle J, which means MJ equally, so FE is a common chord of the circle J and circle M. Then we know that MJ equally divide the chord or arc FE, which means T is a midpoint of the arc FE, which means angle FAT equals to angle TAE. So I hope this is obvious when I demonstrate it. Let me repeat that again. The circle M is the center of the circle M, which is a circle BFEC, right? And the circle J, FE are also on the circle J, meaning that FE is a common chord of the circle J and circle M. And J is the center of the circle J, M is the center of the circle M. So MJ is perpendicular to FE, right? The connection of the centers are perpendicular to the common chord. So the T is the intersection point of MJ to the circle J. So we know that T is a midpoint of the arc FE, which means AT is an angle bisector of angle FAE. So AT is an angle bisector of angle BAC. Okay, that's a problem 7. And now we have circle J meets AA1 on A0, then A0, A2 passes through the midpoint of EF, point F. What is the midpoint of EF? What is the midpoint of EF? It's actually this point, right? The intersection point of EF and JM. So the question is that we connect A and A1. We connect A and A1, meet the circle J on another point, call it A0. And we want to prove that A0 and this point L and A2 are collinear. We want to prove this one. So think about like this. If we want to prove A0, the midpoint of FE, right? The midpoint of FE and A2 are collinear. Just look at, we already proved that triangle A2FE is similar to triangle A2BC. Right? Let me say that triangle A2FE is similar to triangle A2BC. Right? And let's consider about the triangle A2FA0. Right? A0 is the intersection point of circle J to AA1, and we know that AA1 is a diameter of the circle O. Circle O point O is here, A0 is here. So basically, A0, O, A1, these 4 points are collinear, right? O is here. Now the question is, what about the triangle A2FA0? Because angle FA2A0 equals to angle FAA0, which is angle BAA1, which is angle BA2A1, right? So we know that angle FA2A0 equals to angle BA2A1. Basically, BA2 is the angle bisector of angle FA2A1. Right, so we know that this angle equals to this one. And if we look at the angle A0FA2, it equals to angle A0AA2, which is angle A1AA2, which equals to angle A1BA2. Right, that is saying the angle A0FA2 equals to angle A1BA2, which means triangle A2A0F is similar to triangle A2A1B. Now the problem is very interesting. If you think about these two sets of the similar triangles, we know that triangle A2FE is similar to triangle A2BC, and we know that triangle A2FA0 is similar to triangle A2BA1. Right? Now, if you look at the circle J and circle O, circle J is a circumcircle of the triangle A2FE. Right? Circle J, it's very important. Circle J is a circumcircle of the triangle A2FE. And circle O is a circumcircle of the triangle A2BC. Right? Now, we also know that if you look at the angle let me say it this way. So actually, why don't we just draw it? It's very interesting here. So we have a circle J like this. We have a circle J like this. We have circle J here. I just try to move the figure here. So we have A2 here. And we have FE here, right? And we have, this is circle J. And we have A0 here. That is A2FA0 and A2FE. And for another set, we know that so BC is here, and also this is A1. Okay, look like this. So basically, what I'm trying to say is that if you look at the relation between these two sets of the similar triangles, we have the triangle A2FE similar to triangle A2BC, and we have triangle A2FA0 similar to triangle A2BA1. Right, and look at the relative position of these two sets of the similar triangles. So for the triangle A2FE and triangle A2FA0, they're sharing the side FA2, which is a similar side in the triangle A2BC and triangle A2BA1, right? So this side. So basically what I'm trying to say is that triangle A2FE and triangle A2FA0, they're sharing the side FA2 and these two triangles are on the same side. So the triangle A2BC and triangle A2BA1, they're sharing the side BA2 and also on the same side, which means these two triangles, they are homothetic. I mean, these two sides of the triangles, they're homothetic, and then we can think about the position of the point of the M, right? This is the point M. In the side of the A2B, A1C, these two triangles, we know that A2A1 and M are collinear. M is the midpoint of BC. And because this triangle, the A2FE, because they are homothetic, that directly tells us A2A0 and FE intersects on the midpoint of FE, right? Because of the homothetic. So that means this L is a midpoint of FE. So which means JM, FE, and A0, A2 are concurrent on the midpoint of FE, which is L here. Okay, I hope you can get it. Now we finish this one. Let's see the next one. ME, MF are tangent of circle J. And also we want to prove that HEA to F is a harmonic quadrilateral. Okay, we want to, let me zoom in this figure. Now we want to prove that MF and ME are tangent of the circle J, right? It's actually easy to prove because MDEJF are cyclic, right? Because they are all on the 9-point circle. MDEJF, they are all on the 9-point circle. And because angle MDJ equals to 90 degrees, so we know that MJ is the diameter of the 9-point circle, which means angle MEJ is 90 degrees and angle MFJ is 90 degrees. JE is a radius of the circle J. JF is the radius of the circle J. And we know that angle MEJ is 90 degrees and make ME to be the tangent of the circle J. And we know angle MFJ is 90 degrees. So MF is a tangent of the circle J. Just to recognize that MDEJF are cyclic, right, on the 9-point circle. And we want to prove that HEA to F is a harmonic quadrilateral. We want to prove HEA to F. HEA to F is a harmonic quadrilateral. Please refer to my video, talk about harmonic quadrilateral harmonic array. That video is quite important. Please refer to that. If you refer to that, then we can directly use a property from that video. We already know that M can be taken as a point outside of the circle J. And because MF, ME are the tangent of the circle J, and because MHA2, right? MHA2, HA is a chord that's passing through M. So we know that based on the property and all the proof I've shown in that video, we can directly say FHEA2 is a harmonic quadrilateral. Okay. Please refer to that video. That is a very important video, and it's a very important property, harmonic quadrilateral. And now we want to prove that A2H and EF meets on K, and MKHA2 is a harmonic array. See, FE and HA2 meets on a point K. We want to prove that MHKA2 is a harmonic array. Again, we don't have to prove it. It would take another like 20 minutes. It's just directly the property of the harmonic quadrilateral. I've shown that in the talk about the harmonic array, harmonic bundle video. Please check on that. Okay, prove that circle J meets a circle HBC on G, then AGM are collinear. It's actually, we've already done that because we proved that BCHS are cyclic, right? We proved that BCHS are cyclic. Here, that the circle J meets a circle HBC. That is on point G. The point G is actually the point S here. And we already know that ASM are collinear, so AGM are collinear. Okay, so in this video, I finished the rest part from the geometry treasure about the same figure, the property of the same figure. So in total, we discussed more than 20 properties, I believe. And this figure is an interesting figure. So we call it property, but it's actually just a bunch of problems. Each one is not like extremely difficult, but if you combine all of them, it would take some time to finish all of them, especially for this one, that AT is for me, to prove that AT is the angle bisector of angle BAC is the one that take me longer because I didn't notice that MJ can be seen as the connection of the centers of the two circles, and directly we get that MJ is perpendicular to FE. So it's actually if you observe that, it's a very simple question. Anyway, all of these properties I've shown, it's not like I'm trying to show you the simplest solution or fastest solution. I'm trying to work through a problem with you to show the way that I approach. It may not be the simplest, and it shouldn't be the simplest, because when you try to solve a problem, you'll never know what is the fastest way, right? You can only know the fastest way when you finish solving this problem and look back and have some insight of the figure. Then you can find the fastest way to solve a problem, right? So some audience give me the feedback saying that, oh, you can directly jump some steps. The problem is that when I solve this problem, I may not jump those steps because I want to collect as much information as possible to solve a hard problem. You can never like doing a research or doing a geometry problem, you can never on a path without any extra or redundant information, right? That's impossible, and that's not the correct way to constrain yourself. Anyway, I hope you like this video. See you in next one. Thank you.